Hi, this is Lisa Knight. This is the first of 3 lectures on the refraction of light. The refraction of light refers to the bending of light as it goes into another substance. Remember that light travels at 3 times 10 to the 8 meters per second in a vacuum and in air. However, when it travels into something that's considered more optically dense, it will slow down and it causes it to either bend. Consider a piece of glass that you're looking through. Light that hits the surface of the glass is moving from air where it's traveling at 3 times 10 to the 8 meters per second. And when it enters the glass, it slows down significantly. So it bends, and as a result, it bends towards the normal. The angle of incidence is measured just like it was for mirrors with respect to the ray of light that's hitting the surface and the normal to the surface. The angle of refraction is measured with the refracted ray between the refracted ray and the normal. Notice that angle of refraction is much smaller than the angle of incidence because it's slowed down. When it returns into the air, it will speed right back up to 3 times 10 to the 8 meters per second. So if it enters at 30 degrees, it'll bend significantly, maybe down to even 19 degrees, and then it'll come back out at 30 degrees. This explains why when you look out in a mirror, you can see pretty much exactly what you see, what is out there, right? The objects that you're looking at are looking identical, right? You don't have any distortion unless the glass is old and has warped. So how fast does light travel in different substances? Well, that depends on that optical density I referred to. It's called the index of refraction, N. N is simply the ratio of the speed of light to the speed in that substance of light. It has no units because it's just a ratio of speed to speed. But for example, diamond has an index of 2.42. So that means that the speed of light in air is more than twice that of the speed of light inside the diamond. To calculate that, all you would have to do is look up the index of refraction and plug and chug into the formula. So the velocity is going to be equal to the speed of light divided by the index of refraction, which gives us a speed of 1.2 times 10 to the 8 meters per second in a diamond. Also, because it slows down, there's a law that helps us determine what the angle of refraction will be if we know the angle of incidence. It's called Snell's law. So you always have 2 substances that you're dealing with, an interface. For example, if a ray is going into water, it's hitting the water from the air. So you're going from air to water. Air has an index of 1, and water has an index of 1.33. So if a ray of light is incident at 60 degrees, then it's going to go into something more dense, and it will slow down, and it will bend towards the normal. So to find that angle of 40.6 degrees, you would simply take 1 times the sine of 60 equals 1.33 for water times the sine of theta 2, and solve for theta 2. Notice that diamond has a much higher index of 2.42, and it bends a lot more. So take an example, light incident on a pond. So you're going into water from the air at an angle of incidence of 30 degrees. What is its angle of refraction? So we would set this up as going from the air to the water. So 1.00 times sine of 30 equals 1.33 times sine of x. we would take the inverse sine, get the angle. It's going to give us 22.1 degrees. Make sure your calculator is in degrees. So when a ray of light enters a medium where its speed decreases, it's bent towards the normal. When a ray of light enters a medium where its speed increases, it is bent away from the normal. There is no change in direction of propagation if there is no change in index of refraction. The greater the change of index refraction, the greater the change in propagation direction. If a ray of light goes from one medium to another along the normal, it does not bend at all. Refraction can make objects immersed in water appear broken and can create mirages. So do this at home. Take a pencil or a spoon and put it in a glass of water and look at it from the side. It looks like the spoon or the pencil is broken, but in fact it's not. It's only that way because light bends towards the normal, which gives it that broken effect. What happens? We know that when light enters a lower index, it'll be bent away because it speeds up. So imagine that you have got light at the bottom of a pool, and it's hitting the water-air interface, and it's going from the water to the air. So at some angles, it will just go out into the air and be bigger than the original angle, right? But as that angle of incidence gets bigger, the angle of refraction gets bigger. And there's actually a critical angle where the angle of refraction will be 90 degrees. And if light enters at anything bigger than that, it'll actually bounce back into the water. This phenomena is called total internal reflection. This is how fiber optics works. We send in a beam of light, well, actually we send an electrical signal in pulses of light into an optical fiber. And when it hits the side of the fiber at an angle bigger than that critical angle, and it bounces back inside. And it stays inside the core. This is what is the basis of all our telecommunications now, right? In terms of, our computers and everything, we have all these optical fiber lines everywhere. So what would be the critical angle for a diamond or for water? Remember that the critical angle occurs when the angle of refraction is 0. And it can only occur if you're going from the denser substance into the lighter substance. So if you wouldn't draw the picture going from air to water, you would draw the picture starting in the water and going into the air. So we want to find that angle where the angle of refraction will be 90 degrees in the air. And if we put it in, if the light hits it at any greater angle, it'll just bounce right back into the water and stay in the water. So for a diamond, the way we would set this up is we would say, or since we're going from the water, we would go from 2.42 times sine of x, that's our critical angle that we're looking for, equals 1 times sine of 90, because we're in the air and it's bouncing out at 90 degrees. When we solve that, we get for diamond a 24.4 degree angle, critical angle. So that means that if light is trapped inside of a diamond and it hits the surface of the diamond air interface at anything greater than 24 degrees, it's going to bounce right back into the diamond. Well, let's compare that to what happens in water. Water has a smaller index, so we would expect the critical angle to be a lot larger. So when we set that up, and we set it up the exact same way, except we change the index of refraction to 1.33 times sine of x, we get x to be 48.7 degrees. So that means that in this body of water, if light hits right at 48.7 degrees, it'll just travel along the interface. But if it hits at anything greater than that, right, it'll bounce back in. So water doesn't sparkle as much as diamonds do. Diamonds are beautiful because they sparkle. The reason they sparkle is because they have a high critical angle, and it's much more likely, a low critical angle. It's a lot more likely that when light enters the diamond from outside, that it'll get trapped inside of it, because it's very likely that it's going to enter and it's going to slow down to an angle that is bigger than 24 degrees. And if it does that, then it'll bounce right back inside the diamond, and it'll just kind of stay trapped in the diamond. That's why diamonds are so pretty. You can make it even better if you put some facets on it. So the diamonds that have lots and lots of facets, corners that are shaved off, are much more likely to take advantage of that internal reflection and, be really bright and shiny and sparkly. Water, on the other hand, doesn't have the same appeal. I mean, it does reflect a lot of light to your eyes, and so it can be kind of blinding if the sun hits it just right. But in terms of keeping light inside of it, it's a lot harder, because light would have to hit at something greater, would have to hit that inside at something greater in this area of 48.7 degrees. There's a special angle also called the Brewster's angle. So in the previous slides, you may have seen, and I'll go back to one, here we go, where, actually that's not it, where I showed that there was some light being reflected off, right? And that's because there is a special angle where light will go, some of the light will go in, but some of the light will bounce off according to the Brewster angle, and it actually will bounce off, and it'll be polarized. So a lot of the the light that bounces off the surface of your car is bouncing off at you, and it's polarized, and so it helps for you to have polarized glasses on in order to block that light out.